So Shearer's lemma extends the subadditivity of Shannon entropy, and the statement is the following. Let n, m, and k be natural numbers. Let x1 up to xn be discrete random variables. And we denote by n in brackets the set whose elements are 1 up to n. Let S1 up to Sm be subsets of the set n in brackets, where every element I between 1 to n belongs to at least k of the subsets. And let us denote x with superscript n to be the vector, the random vector x1 up to xn, and x sj to be the subvector with the indices that are the elements of the set S sub j. So what Shearer lemma says is that k times the entropy of the vector x, of the wall vector x1 up to xn, is less than or equal to the sum of the entropies of the subvectors x sj, where j goes from 1 to m. And this lemma appears to be very helpful. It specializes in particular to the subadditivity property of the Shannon entropy. So this is just obtained by letting n be equal to m and taking S sub I to be the singletons that include, where every Si includes just a single element I. In that case, every element belongs only to one subset. So by Shearer's lemma, we get the subadditivity property of the Shannon entropy for discrete random variables. However, we know that the subadditivity property applies also to, in general, also to continuous random variables. So as we will see shortly, if every element I belongs to exactly k of the subsets, then Shearer's lemma also applies to continuous random variables, while the entropy is replaced by the differential entropy. And therefore, by the suggested setting, it follows that Shearer's lemma yields the subadditivity property of the Shannon entropy for discrete as well as continuous random variables. Now, the proof I'll go very briefly, because it's simple and the ideas extend later. So by assumption, let us write the degree of I to be the number of subsets S sub j for which the I element is contained in the subset Sj. So by assumption, the degree of I is larger than or equal to k for every element I. Now for a general set S, subset S, let its elements be I1 up to I sub L in increasing order. So the cardinality of S is L, and S is a subset of n in brackets. And let X sub S be just the subvector whose elements are, whose entries are xi1 up to xil. So here we use the chain rule. And then we rely on the fact that conditioning reduces entropy. So instead of, for example, looking at the entropy of xi2 given xi1, we just look at the entropy of xi2 given all the past elements x1 up to xi2 minus 1. So this is a lower bound, and therefore we get that hxs is lower bounded by this sum, which can be written in this way, where this is the indicator that I belongs to S. Okay? So it is just the fact that we use the chain rule for entropy and the fact that conditioning reduces the entropy. Now, let's apply it to the subsets S sub j. So because we sum over j from 1 to m, we get here a double summation. And then we just swap the order of the summation so that the inner sum, which is j goes from 1 to m, only applies to this first term. And the summation gives just the degree of the element I, which by assumption, the degree of the element I is larger than or equal to k. Now, because we deal with discrete random variables, the conditional entropy is non-negative, and therefore we get an inequality in that direction, and then use again the chain rule to get that it is lower bounded by k times the entropy of the vector x, the whole vector x. So we see here that according to the proof, that we rely here on the non-negativity of the entropy, and therefore this is why we assume that the random variables are discrete. However, if you look at the proof, suppose that di is equal to k for every I, which means that every element I belongs to exactly k of the subsets, then in that case, the inequality will be replaced by equality, irrespectively of the non-negativity of the entropy. Which means that in that case, where we assume that every element I is included in exactly k of the subsets, Shearer's lemma also applies to continuous random variables, and then we can replace, in that case, the entropy by the differential entropy, and use again the chain rule to get the result. So we saw this proof also to validate the fact that if the random variables are continuous, then Shearer's lemma can hold, but under the stronger assumption that that every element I is in exactly k of the subset, not at least, but exactly. So this is what I just said about the extension of the proposition to continuous random variables under the further assumption, the stronger assumption. So let's look at the following simple example that shows, in spite of the simplicity of Shearer's lemma, how it can be applied, not necessarily in information theory, meaning problems related to compression or channel coding, etc. But here it is a geometrical simple problem. So let P be a subset of the three-dimensional Euclidean space, and assume that P is finite, and the number of distinct projections of this subset, of this set P, over each of the planes x, y, x, z, and y, z, is at most R. So there are at most R distinct projections on each of the planes xy, xz, and yz. And the question is, how large can the set P be? So by intuition, it may appear that the largest set P in that case is a lattice. And if R is a square of an integer, then we have square root of R points in each dimension. So you may already guess that the size of the set P is no larger than R raised to the power of 3/2. Square root of R times square root of R times square root of R, which is R raised to the power of 3/2. Yeah, and with equality in the case that it is a lattice. So let's see how it follows by Shearer's lemma. Well, by Shearer's lemma, we have this inequality. 2 times the entropy of xyz is less than or equal to the sum of the entropy of xy plus the entropy of xz plus the entropy of yz. So we see that x appears here twice, y appears here also twice, and z appears here twice. So in that case, it applies also to continuous random variables, but we need it in the discrete setting. So I write this inequality. And now let's assume that a point xyz in P is selected uniformly at random. So the entropy of xyz is the logarithm of the cardinality of P. According to our assumption, the set P has at most R distinct projections on each of the planes xy, xz, and yz. So each of the entropies, entropy of xy, entropy of xz, and entropy of yz, are all less than or equal to log of R. So in total, we get the 2 times the logarithm of the size of P is at most 3 times the logarithm of R, and then by exponentiating both sides of this inequality, we get the bound that the size of P is not larger than R to the power of 3/2. And we know that if R is a square of an integer, then this upper bound is tight and it is achievable for a lattice. Okay, so let's move to a second version of Shearer's lemma. So assume that xn is a discrete n-dimensional random vector, and S is a subset of n in brackets. It is a random subset, and it is independent of the vector xn, x1 up to xn. And let's assume that the random subset S has an arbitrary probability mass function P sub S. Now, if there is a positive theta such that the probability that I belongs to this random subset S is larger than or equal to theta for every I between 1 to n, then the expected value of the entropy of the subvector x sub s, where the expectation is over the choice of s, is larger than or equal to theta times the entropy of the vector x, the whole vector x. So here we have a single subset, S, which is picked at random, subject to an arbitrary probability mass function. And we have this assumption that every element I is contained in S in probability that is at least this number theta. So the proof is much similar. We start with the inequality that we derived earlier. Yeah. And again, we need this, we assume discrete random variables. So we just take the expectation with respect to the probability mass function of S, and then swap the order of summation so that the inner sum is the probability that I belongs to S, which is, according to our assumption, lower bounded by theta. And since the conditional entropy is non-negative, then we get by the chain rule this result. So this is another useful form of Shearer's lemma. Yes, and it applies also to continuous random variables in case that the probability that I belongs to S is theta for all I, which means that it does not depend on I, and equality here is achieved. And then we can replace the entropy by the differential entropy. Now, let's see how it can be applied in the context of graph theory. So let G be a simple graph on n vertices, and denote by M sub L to be the number of induced subgraphs that are complete. Yeah, so I didn't, a complete graph is just a graph on n vertices where every pair of vertices are adjacent. And we also assume that the graph is simple, so it does not have self-loops or parallel edges. And we also assume that the graph is undirected. So under these assumptions, if G is a simple graph on n vertices, we can relate the number of complete subgraphs of different orders in the graph G. So if L and R are just two numbers between 2 and n, we have that this inequality is satisfied. M sub R is, again, is the number of induced complete subgraphs of order R, yeah, where R is larger than L, so it satisfies this inequality. And let's see how this result can be obtained from the second version of Shearer's lemma. So we label the vertices of G by the elements of the set n in brackets, because we have n vertices, and we select two arbitrary integers, L and R, in that range. Now, let x1 up to xr be random variables that are selected uniformly at random as the vertices of any complete induced subgraph of order R in G. Okay, so say G has a complete induced subgraph of order R. Pick one of these complete induced subgraphs of order R, and then select the vertices by randomly labeling them, x1 up to xr. Okay. So if MR is the number of induced subgraphs KR in G, then the entropy of x1 up to xr is the logarithm of r factorial times m sub r, because there are m sub r complete subgraphs in G of order r, and we can label the vertices of every such subgraph in arbitrarily, but just there are r factorial ways to label the vertices of each such induced subgraph of order R. So in total, we have R times MR possible labelings, and since we have here an equiprobable distribution, then the entropy of x1 up to xr is the logarithm of the number of possibilities. So now let S be a uniformly selected subset of size L from 1 up to R in brackets. Then, because by construction, the probability that I is contained in S is just the ratio L over R. Yeah, we start from a set of size R. We pick at random, uniformly at random, a subset of size L. So the probability that I belongs to this subset S is L over R. Now, by using Shearer's lemma, the second version of Shearer's lemma, the parameter theta is L over R, and we have that the entropy of x1 up to xr is the logarithm r factorial times m sub r. So we get this lower bound on the entropy of the expectation of the entropy of the subvector x sub s. Okay, so if this holds with in expectation, it means that there is a certain subset T of size L that satisfies this inequality. So this is exactly what is written here. There is a subset T that is a subset of this R in brackets, and its size is L, for which this inequality holds. But also a subgraph of a complete graph is also a complete graph. So x sub t is supported on a KL complete subgraph. So we have this upper bound on the entropy of x sub t, which means that by combining these two inequalities, we get that inequality, and then rearranging terms, we get the result that was written here, the inequality that was written here. So this is a simple application of the second version of Shearer's lemma in order to get some connections in graph theory about the cardinalities of about the number of complete subgraphs of a given order. So let's see a specific case. If we take L to be 2 and R to be 3, then M sub 2 is just the number of edges, and M sub 3 is the number of triangles in the graph, right? So as a special case of what we have just proved, we get that the number of triangles is at most 1/6 times twice the number of edges raised to the power of 3/2. And this can be also proved independently by spectral graph theory if we rely on some simple identities that relate between the eigenvalues of the adjacency matrix of G and the spectrum is just the eigenvalues, the multiset of the eigenvalues of the adjacency matrix of G. So let's write them by lambda J. Then we know that the sum of the squares of these eigenvalues is 2 times the number of edges, and the sum of the squares, sum of the cubes of the eigenvalues is 6 times the number of triangles. And it gives us that 6 times t is less than or equal to 2 times e raised to the power of 3/2, which is exactly the inequality that we have stated. Yeah, but this inequality is more general because it deals with any values of L and R. Here we tested it for the case where L is 2 and R is 3, and prove it also by spectral graph theory. Okay. So now I would like to talk about an application that is related to a set of read K functions and especially read K Boolean functions. So a set of read K functions is a set of functions where each input variable appears in the argument of at most K different functions within that set. So in other words, each variable can only be read or accessed by at most K functions. Okay? So if we write it in the terminology of subsets, and we have a set of functions, fj, where j goes from 1 to m, whose arguments are x1 up to xn, and it is read K if there exist subsets S1 up to Sm, all of them are subsets of L in brackets, such that Fj depends on the subvector x S sub j, where the degree of I in these subsets is at most k. So this is just another way to express the definition of a set of read K functions. And now you can see how it relates to Shearer's lemma. So this proposition is the probabilistic result on read K Boolean functions. Let m, n, and k be integers with k less than or equal to m, and let S1 up to Sm be subsets of N in brackets, where every element I belongs to at most k of the subsets. Yeah. So let Fj be a set of read K Boolean functions, where Fj is a mapping from 0, 1 raised to the power of the cardinality of Sj to the two elements at 0, 1. So it is a read K Boolean function because of the assumption that every element I belongs to at most k of the subsets S sub j. And now let x be x1 up to xn be a binary random vector that is uniformly distributed on the Hamming cube 0, 1 raised to the power of n. And let yj be defined to be yj is fj of x S sub j. Okay? Now, denote by pj to be the probability that yj is equal to 1 for all j between 1 to m. Then, the probability that this vector is a vector of all ones is at most the product of pj raised to the power of 1 over k. Okay? So let's see first a simple special case. Assume that the subsets S1 up to Sm are disjoint subsets, and every element I belongs to exactly one of these subsets. In that case, the random variables yj are independent So the probability of y1 to be equal to yn to be equal to 1 is just the product of pj, because these are independent random variables. So in that case, k is 1, indeed, because every element in this special setting belongs to only one subset. And then this inequality is achieved with equality. So Shearer's lemma enables to extend this simple result also to read k Boolean functions, yeah, where the random variables yj are not necessarily independent. But there is a certain assumption, yes, about the subsets S1 up to Sm, in the sense that every element I belongs to at most k of these subsets. Yeah, and the proof is, well, it relies on Shearer's lemma. Maybe I will not go into the details, but you just define yj to be fj of x as j, and you define A to be the number of points in the Hamming cube such that y1 up to ym is 1, and aj to be the number of subvectors for which yj is 1 for every j between 1 to m. And then Shearer's lemma is applied by defining an auxiliary random variable z to be uniformly distributed on A. And yeah, so by the assumption and the simple arguments that are written here, one relies on Shearer's lemma, and the other one is just the entropy of this uniformly distributed vector. You get the result that is stated here. Okay. Yeah. So this is the special case that I just considered at the beginning to give the motivation for this extension. Yeah, and here it can be applied not necessarily for y to be equal to the all one vector, but if S is just a subset of the Hamming cube, then you can get an upper bound by additivity or on the probability that vector y belongs to this set S. So let's see an example, a nice example. So let G be a random graph on n vertices, where any two vertices are independently adjacent with probability 1/2, and let EV, E sub V, be an event which depends on the edges that are incident to a vertex V in the set of vertices of G. So E sub V is just an event that only depends on the edges that are incident to that vertex. So an HE in the graph, in this simple graph, can only affect two of the events, which is EV1 and EV2, where V1 and V2 are the endpoints of the HE. So by construction, the edges are statistically independent, and let Y sub V be the indicator of the event E sub V. Then every HE can influence at most K equals 2 of the binary random variables Y sub V, where V goes over all the vertices of the graph. So in that case, we have K equals 2, And by applying this proposition that we just proved or stated, we get that the probability of the intersection of E sub V over all V that goes on the vertices of G is upper bounded by the square root of the product of the probabilities of each of the events E sub V. Okay, so this is a nice application of the proposition that we have just stated for read K Boolean functions. So we see that how it can be applied to get a probabilistic result for random graphs. Yeah, so Shearer's lemma can be also applied to the relative entropy. And the statement is quite similar if x1 up to xn are discrete random variables, and u1 up to un are independent random variables, where ui has equiprobable distribution over a set containing the support of xi. And now, if S1 up to Sm are subsets of n in brackets, such that each element I is contained this time in at most k of these subsets, then this inequality holds. So you see that the direction of the inequality was changed. And also here, instead of at least, it is written at most. So it relies on the chain rule and the simple identity that the divergence between a distribution, the distribution of x, and the distribution of a uniformly distributed random vector, u, is just the difference of the entropies, and then you apply Shearer's lemma and Shearer's lemma here, and also the fact that ui are independent, so you get here the additivity property, and combining both gives the required inequality here, that is Shearer's lemma for the relative entropy. Now, we can apply it in the context of read K functions. So let's just define the binary relative entropy to be the relative entropy from one Bernoulli distribution to the other Bernoulli distribution with parameters P and Q respectively. And as an application, we get a Chernoff-like bounds that rely on this Shearer's lemma for the relative entropy. So in that case, let m, n, and k be integers with k less than or equal to m, x1 up to xn be independent discrete random variables, s1 up to sm be subsets of n in brackets, where every I is contained in at most k subsets. Let pj be the expected value of yj, where yj is fj x sj. And let P be just the arithmetic average of the probability of the expected values Pj. Then you get a Chernoff-like bound that reads as follows, and you see that the tails of the probabilities are upper bounded exponentially by something which decays with the relative entropy between two probability Bernoulli random distributions. So, and using also Pinsker's inequality, you get also exponential bounds that do not depend on the relative entropy, on the binary relative entropy, but just are more simple. And this is an extension of Chernoff bounds. Here you see that the random variables yj, if k is larger than or equal to 2, the random variables yj are not necessarily independent. Yeah, there is some dependence among the random variables y sub j, but nevertheless, you get this extended version of Chernoff-like bounds. Yeah, so in that case, instead of having exponent of minus m times something, you have the exponent of minus m over k. So if k is 1 and the random variables are independent, then this is the known Chernoff bound. But if k is larger than or equal to 2, then under this assumption of the read k functions, you have an exponential upper bound on the tail probabilities that decay like m over k. So it also enables to get a result on the number of length r cycles in a random graph. So let G be a random graph with n vertices such that any two vertices are adjacent independently with probability p, with a given fixed probability p, and let n sub r of G be the number of lengths r cycles in a randomly selected graph. So it is possible to show by the Chernoff-like bounds that we just presented that these large deviations result holds. So the probability that the number of lengths r cycles in a randomly selected graph G deviates from the expected value by more than epsilon times the expected value is upper bounded by 2 times this exponent. So you see that the larger epsilon is, of course, the decay of the exponent is faster. And it is also possible to express the exact number of the exact expression for the expected value of length r cycles, the number of length r cycles, which is given by this expression. So if we take, for example, r to be 3, then we get that this length 3 cycle is a triangle, and substituting r equals 3 in this result gives a result in the paper by Gavinsky et al. That was published about a decade ago in Random Structures and Algorithms journal. So far we talked about Shearer's lemma, and now I would like to address shortly about generalizations of Shearer's lemma. So one generalization is looking at, instead of the Shannon entropy, just on a more general setting of sub-modular functions. So this is the setting. We have omega, let omega be a finite and non-empty set, and let f be from the power set of omega to r be a real valued set function. So we say that f is submodular if this inequality holds for every two subsets T and S of omega. And if the inequality is satisfied in the reverse direction, then f is said to be a supermodular function. So an elementary property of submodular functions is the following inequality. If S is included in T, which is included in omega, and little omega is in the complementary in the complement of the set T, so it does not it is not an element of S or T, then the larger the set is, the smaller is the increase in F when a new element is added. So you see that S is smaller than T, and the increment that you receive by looking at Fs union with the omega minus Fs is larger than or equal to Ft union with omega minus F of t. So this is a mathematical expression of what is just stated here in words, that the larger is the set, the smaller is the increase in F when a new element is added. A monotone function is just a function where if S is included in T, then Fs is less than or than Ft. And you say that if F is submodular and monotonically increasing, and also the F at an empty set is 0, then you call it a rank function. Now, there are many information theoretic set functions that are sub or supermodulars. Some examples are the entropy, where you look now at F of t to be the entropy of the subvector x sub t. So it is possible to show that for discrete random variables, it is a rank function. And the conditional entropy, where you look at the entropy, conditional entropy of x sub t given x of the complementary of t, then this is a supermodular, monotonically increasing function where the f of the empty set is 0. And there are some other examples of set functions, like, for example, a mutual information is a submodular, and f of the empty set is 0, but it's not a rank function because it is not monotonically increasing, etc. Also, the sum of independent random variables, if you look at the sum of independent random variables, then their entropy defines a rank function. So already, if you look at the information theory context, just considering submodular functions instead of just the Shannon entropy gives a significant extension. Yes, so here it is just shown that the entropy is a submodular function. And one generalized version says that the Shannon entropy, the Shearer's lemma extends to all non-negative and submodular functions. They extend to every non-negative and submodular function, where again, every element in omega is included in at least d of the subsets S sub j. And then it is possible to show a similar inequality that extends Shearer's lemma. Yeah. Another extension of the Shearer's lemma was suggested by Madiman and Tetali, and it appears in the paper Transactional Information Theory from 2010. Here, you not just look at the degree of an element I, but you also look at the minimum or the maximum of these degrees. And then it's possible to get not just only an upper bound on the entropy of the vector x, but also a lower bound that depends on the conditional entropies and on these maximal degrees. So it also gives a counterpart of Shearer's lemma by providing this lower bound in addition to the upper bound on the right-hand side of the inequality. Yes, so it specializes in particular to Shearer's lemma, but we also get this lower bound on k times the entropy of xn, and if every element is included in exactly a fixed number of k of these subsets, we also get it. It is also valid for continuous random variables where entropy is replaced by differential entropy and conditional entropy is replaced by conditional differential entropy. Another thing is related to erasure entropy. So the erasure entropy of the discrete random vector is given by h minus of xn, which is the sum where I goes from 1 to n of the entropy of xi given all the rest of the elements in the vector. So it is the sum of hxi given x1 up to xi minus 1 and xi plus 1 up to xn. So this erasure entropy notion was introduced by Verdoux and Weissman in a paper from 2008. And it is possible to show that the difference between the entropy and the erasure entropy is a sum of mutual informations between an element xi and all the other elements from xi plus 1 up to xn. And this sum of mutual informations is, of course, non-negative. So the erasure entropy is less than or equal to the entropy. Yeah. So, well, applying applying this corollary, it is possible to show that if we take the singletons S sub I to be a singletons that includes just the single element I, then we get these inequalities that reproduce the subadditivity vector, the subadditivity property of the Shannon entropy, and also Han's inequality. Yeah, so this is another setting where we obtain the Han's inequality by looking at all the subsets of cardinality that is exactly n minus 1. Yeah. And it reproduces in particular the Shearer's lemma. So to conclude, we introduced two versions of Shearer's lemmas, Shearer's inequalities. We discussed applications that were geometrical, graph theory, related to read K Boolean functions. We gave probabilistic results in graph theory, a version of Shearer's lemma for the relative entropy, extended Chernoff bounds for independent random variables to Chernoff-like bounds for sums of read K functions. And Shearer's lemma can also be applied to hypergraphs with some interesting consequences in linear algebra. And this is a work by Ehud Friedgut from 2004 that was not covered in this talk. We also addressed generalizations of Shearer and Han inequalities, extension of Shearer inequalities to submodular functions with some links to information theoretic set functions, an extension of Shearer's lemma and Han's inequality and the counterpart of these inequalities, and also provided a connection to the erasure divergence that was introduced by Verdú and Weishman. And we examined some special cases that reproduced the Shearer's lemma, Han's inequalities, and some other counterparts. So that concludes my talk, and I would like to, of course, acknowledge the organizers for inviting me and for providing me the opportunity to give this talk. Also, in a short notice, I could not, unfortunately, very unfortunately for me, attend the workshop in person. So I'm sure that it's a great workshop, and I'm looking forward to see the videos of the other talks. But in the meantime, I would like to also acknowledge you all for waking up in the morning and coming to my talk. So thank you very much.